Hi, welcome to Lecture 15. This lecture is on implicit differentiation. Implicit differentiation is often very confusing for students, but it doesn't have to be. If you think about the word implicit opposed to the word explicit, then it might begin to make some sense, but we'll look at it in a couple of different ways. Implicit differentiation means that you're going to be trying to find the derivative of a dependent variable, usually y, with respect to an independent variable x. And the problem is that, unlike the previous problems that you've had to do, you won't have a formula for y, like y equals blah, 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 blah. Instead, what we're going to have is an equation that involves y in it. So something like 2x squared plus y squared plus 3xy equals 6. Now, the fact that you've got an equation is important here. So let me start all over again and describe what it is that we had before. What we had before was y, which was a function of the independent variable x. So y, the dependent variable, is explicitly written in terms of x, at least just now. So we would have a formula that we could just differentiate. And all we had to really worry about was, like, for instance, 3x squared. And we would just say, okay, we know that the answer is going to be, well, of course the answer is 6x, but we could use the definition of the derivative and figure things because we knew what y was. In this situation, they're not telling us what y is. You don't see in this equation here, you don't see y equals anything. What you see is a y right here, and you see a y right there. And in theory, you could solve this. I wouldn't like to, but I do know how to do it, because if I think of y as the unknown, here's y squared, here's y to the first. Those are the only y's in this equation, and therefore this makes this equation a quadratic equation in terms of y, and I do know how to solve quadratic equations. I could whip out the quadratic formula, but I'm not going to do that. There's no point. That's not the point of this exercise. The point of this exercise is that because of this equation, implicitly, we could get from that equation to another equation that would say y equals some horrible mess we would use, in this case, using the quadratic formula. Well, that's a lot of work, and a lot of times you won't even be able to do it. You could have an equation like this: x times the sine of y plus xy equals 6x plus y plus 7. And see, here, I don't care what you do, there's no way that a human being is going to be able to take that y and that y and that y and untangle them to the point where you could get something like this. There's no formula. There's no way that you can solve this type of equation for y. And yet, because of this equation, in theory, somebody could solve for y, at least in theory. Why is that? Well, because whenever you have an equation, anytime you have an equation, as soon as you set a value for x, as soon as you set a value like of x being equal to 0, then would be determined. In fact, in this case, you can see that if x set to 0, this would all go away, and this would go away, and you'd be left y plus 7 equals 0, and so y equals negative 7. So in this particular equation, you could tell that the point x equals 0, y equals 7 is on the graph of this thing, even though I have no idea what y is equal to in terms of x. I can't solve this equation. But I could figure out that 0, 7 works. Now, once you see what I just did here for this equation, you can get an idea of why a computer can draw a graph of the solution to this equation, even though the computer cannot solve this equation. So all that the computer is going to do is to plug in every x and y on the screen and see if it works. And if it works, it lights up the pixel. It just goes boop. and lights it up, and then it probably finds that other pixels nearby are lit up, and then it draws all those pixels. And probably plays connect the dots so that it draws a graph of what you see there. All right, let's do an example where it's much easier to figure out what's going on because you already know what this thing is. Here's an equation, x squared plus y squared equals 1. You all recognize that equation. That is the equation of the unit circle. So the graph of this looks like this. Now, in this equation, I could solve it for y. Obviously, y squared equals 1 minus x squared, and then y equals plus or minus the square root of 1 minus x squared. And the plus square root is going to give me the upper half of the semicircle, and the minus square root is going to give me the bottom half of the semicircle. So, yeah, I could solve it, and then I could calculate dy dx. dy dx I could calculate by means of the power rule, because this is 1 minus x squared to the 1/2 power, and the chain rule, and blah, blah, blah. So I could do this, and I'd have to do it twice because of this plus or minus, because I have two solutions. And then I could do things like figure out what the slope of the tangent line is at this point. You know, like the point where x is equal to 1/2 and y is equal to, I think that's square root of 3 over 2, isn't it? So I could calculate the slope of the tangent line there just by doing all this work. But there is another way, and that's where this implicit differentiation comes in. If you have an equation, the equation sets up a relationship between x and y, in the sense that if I pick a value for x, y becomes determined. And I want you to, before we go any further, I want you to notice the difference between this situation and this situation. Let's do this on a different page, if I can. Let's do this on a different page. So suppose that I just wrote x squared plus y squared. What kind of thing is x squared plus y squared? I did not write an equation, so this is not an equation. So in all of these problems that we've had so far for finding derivatives, you've had to find the derivative with respect to x, and you've had other letters pop up. And what were you supposed to assume? Well, you're supposed to assume that the other letters are constants. Well, y is kind of special. Y is usually a dependent variable, or you could make it a constant relative to x. In any case, if you're given an expression that's just x squared plus y squared, what are you supposed to assume about y when x is changed? And the answer is, unless they tell you anything different, unless they have anything else earlier in the problem, if they just say, consider x squared plus y squared, what are you supposed to think about y relative to x? In the sense that if I change x, is that going to cause y to change? The answer is no, not with something like this. Something like this you could think of as a function of both x and y. In other words, how could you tell what this thing is equal to? Not until I tell you something for x and something for y. So what this is really, unless I set up an equation, what this is really is a function of two variables, a function of x and y. Now, you will see this in Calculus 3. This will be done a lot. In fact, it's almost the whole course. Functions of more than one variable. That's not where we're going, fortunately. In our case, we have this situation. We have x squared plus y squared equals 1. And this is very different. In this case, if I make a change in x, if I give you a value for x, like if I say x is equal to 0.5, well then y becomes determined. You don't have an infinite number of choices for y. Not two choices, but you're not going to have an infinite number like you'd had over here. If I pick x equals 0.5, you could pick anything you wanted for y, and that would work. Any number at all. You could plug anything at all in for y here, and so what? X squared plus y squared. It makes sense no matter what you do for x and no matter what you do for y, independent of one another. So these two are independent variables in this situation, where you don't have x squared plus y squared equal to something. It's defining here a function of two variables. Here, you have x squared plus y squared set equal to something. And because of this equation, whenever you set x equal to something, that causes y to be determined. Y is determined as a result. So because of this equation, that is what makes y a function of x. Y depends on x because of this equation. If I make a change in x, change x to anything else, then y becomes determined. In fact, if I changed x to 7, in this case, there is no possible y that would work. Right? 49 over here, there's nothing you could put in for y to square it and add to 49 to give you 1. 7 wouldn't work. But, I could put 0.8 in for x and then figure out what y would work. And then I could put 0.1 in for x and figure out what y would work. So each time I change x, it causes a change in y. Y depends on x. So y is a function of x whenever you see it in an equation with x present. So whenever you see a y in an equation, you've got to think that is not just a simple variable, that is something that depends on x. So y is not a simple variable, y is a dependent variable, y is a function of x, all by itself. So if you wanted to, you could think of it this way: x squared plus f of x squared equals 1. Now that might seem like a very silly way to think of things, but the problem is, we'll go back to the first page here, maybe. The problem is that we want to calculate derivatives. So our problem is to find the derivative of y with respect to x, to find dy dx, right there. So how do we find dy dx when we don't even know what y is? We have an equation like this, or we have an equation like this that has a y in it, and therefore y is a function of x. So let's go to a simple situation, really simple, even simpler than this circle. Let's suppose I go 2x plus 3y equals 4. All right, in this, maybe that's too simple. Well, all right, we'll go ahead and do it. 2x plus 3y equals 4. I know that I could solve this equation for y, but I want to do it in another way. I want to go ahead and say, if these two things are going to be equal to each other, couldn't I say then that the derivative of the left would be the same as the derivative of the right? After all, if these two things are equal, their derivatives are going to be the same. So what I'm saying is the derivative with respect to x of 2x plus 3y would have to be exactly the same as the derivative with respect to x of 4. Now obviously the derivative with respect to x of 4 is 0. But what's the derivative with respect to x of 2x? Well, what's the derivative with respect to x of this? Well, what kind of thing is this? This is a sum. So the derivative of a sum is the sum of the derivatives. So I would get the derivative of 2x, which is 2, plus the derivative of 3y. But wait a minute, what is the derivative of 3y? Well, here's where I've got to be careful to remember what is y. What is y? Is y the independent variable? No, it is not. So y, all by itself, is a complicated function. It's f of x, even though I haven't solved for it. So, what is the derivative of 3y? Well, what's the derivative of 3 times anything? 3 times the derivative of that anything. And I don't know what y is because I didn't solve for it. So all I can do at this point is to say the answer for the derivative with respect to x of y is the derivative of y with respect to x. That's like duh. Y is a function. It's not x. It is a function of x. All by itself, y is some complicated function of x. So if I take derivative with respect to x of y, I get the derivative with respect to x of y. Yes, it's that stupid. It's that simple. But now look what I can do. I can solve for dy dx. dy dx equals, obviously bring the 2 over to the other side, divide both sides by 3, and I have solved for dy dx. Notice I never solved for y. Now, of course, I could go from here and solve for y directly. 3y equals 4 minus 2x, and y equals 4/3 minus 2/3 x, and then calculate dy dx from here using all the rules that we know, and obviously the derivative of 4/3 is 0, and the derivative of minus 2/3 x is minus 2/3. So we get the same answer. But we got the answer this way without ever solving for y. And this is a remarkable thing. We can calculate dx even when I can't give you a formula for y. Like in these cases up above here, in this kind of situation, certainly in this kind of situation, I cannot solve this equation for y. But I could tell you what dy dx is at this point, because I can calculate dy dx from here. Now this will be a lot more complicated to do. So if we want to try this equation, let's build up to it. Let's build up to it by trying something a little bit simpler. All right? So let's try another example, which is not going to be so bad. Let's try let's try this one, in fact, x squared plus y squared equals 1. So I want to calculate dy dx from x squared plus y squared equals 1, even though I could solve this for y. But it's going to be much easier to do it by this implicit differentiation, except that, as you'll see, we have a trick to worry about. We have one problem to worry about. So this is the graph of x squared plus y squared equals 1, unit circle. And let's make a really simple example. You all know what this point is. This is the point where x equals 0, y equals 1. And I want to know what the equation of the tangent line is right there. Well, duh, it's going to be horizontal, so it's going to be y equals 1. But let's just see what happens if I didn't know that. I need to know what the derivative is. I need to know what dy dx is. So I want to find dy dx. And I'm going to use this equation and use the idea of implicit differentiation by doing what I did a minute ago. Namely, take the derivative of both sides with respect to x. So I'm going to write it that way. The derivative with respect to x of x squared plus y squared is going to be the derivative with respect to x of 1. So once again, on the right, I have 0 because the derivative of 1 is 0. And on the left, I have to take the derivative of the sum, which is the sum of the derivatives. Derivative of x squared is 2x, no problem, because x is the independent variable. And here's the problem. What's the derivative of y squared? Well, you got to remember what y is. What is y? Y is a function. Y is the dependent variable. Y depends on x. How come? Because of this equation. Because if I change x, y has to dance as a result. If x moves, y has to move. So y depends on x. Well, I'm getting a little distracted here mentally because I'm thinking, well, x depend on y? Well, yes, it can. But the reason that I'm thinking about it as y depending on x is because the question was find dy dx. I could have asked find dx dy, and then everything would have been reversed. We'll talk about that later. For now, y is simply going to depend on x. So when you come to take the derivative of y squared, what are you talking about? You're not talking about the independent variable, so you can't do it by just going to y, because y is a function. So you're really looking at this. how do you take the derivative of this? And the answer is 2 words, the chain rule. You use the power rule here because it's 2 times y. I'm not going to write f of x. 2 times whatever's there. But the chain rule says you got to multiply by the derivative of what's inside. So this is going to give you the derivative of y with respect to x. The derivative of what's inside is f prime of x, which of course is the same as dy dx. So here's an equation, and it's got a dy dx in it. And I can solve this equation pretty easily. Divide both sides by 2, move the x to the other side, so dy dx is going to be equal to minus x divided by y, which is kind of a cool formula. It tells me that the slope of the tangent line on the unit circle anywhere is the negative of the x value divided by the y value. And if you think about it, like here, what's the slope of the tangent line? Well, here at a 45-degree angle, the x and the y are equal, so you're dividing 2 equal numbers and you get 1, and you get a minus. Well, of course, the tangent line slopes down. How about over here at a 45-degree angle? Well, if this is 45 degree, the x and the y are equal but opposite, because the y will be positive, but the x is measured negatively. So the answer will be 1. I'm sorry, negative 1, but you got a minus here, so it's going to actually end up being positive 1, which matches. You can work that through. You can also see that it is going to give me the 0 that I wanted here, because the x is 0 and the y is 1. That's not a problem. That gives you 0. If you go out here to the right, the tangent line will be vertical. That's bad news. Vertical lines don't have slope. And in fact, here you would have y equals 0 in the denominator. So this makes perfectly good sense. Okay, time to do bunches of problems. Actually, I think maybe we should do one more before we attempt that nasty one at the beginning. Let's look at a problem like this. We want to find dy dx. Find dy dx, or after a while you're going to want to use y prime instead of dy dx because it's a lot quicker to write it. And here's all you know. All you know is that e to the x sine x equals x plus xy. That's all you know. Well, of course, because this is an equation, you can see that... Is this the problem? I'm copying it from the book. Yeah, this is the problem. Actually, this could be solved for y pretty easily. But it's actually still simpler to do it, I think, by implicit differentiation. Oh yeah, this one's going to be very easy. Well, we'll go ahead and do it. So we have to take the derivative of both sides with respect to x. So the derivative of e to the x sine x will be the same as the derivative with respect to x of x plus xy. So on the left, how do I take the derivative of e to the x sine x? What kind of thing am I dealing with? It's a product. So I have to use the product rule. So I get the first times the derivative, and derivative of sine is cosine, plus the second, sine x, times the derivative of the first, which is, of course, e to the x. So that takes care of the left side. What's the derivative of the right? The derivative of this thing, x, is 1, no problem. But what do I do when I get xy? What kind of a thing is that? Well, neither x nor y is a constant, and we're multiplying them together, so I have to use the product rule. Okay, carefully now. Take the product rule and you say the first times the derivative of the second. What's the derivative of y? Well, the derivative of y is the derivative of y, dy dx. Because y is not x. Y is a function of x. You got to think whenever you see y, it's some horrible function that I don't even know. Look at this equation. You can see that y is going to be this thing minus x divided by x. So it's going to be pretty nasty. We could see what it is, but it's not something I really want to deal with right now. In any case, when I take the derivative of y, I just get the derivative of y. Okay, first times the derivative of the second plus the second times the derivative of the first. The derivative of x now, with respect to x, is just 1. Okay, so from here, I can solve for dy dx. I throw everything else over to the other side. So I have e to the x cosine of x plus sine x e to the x minus this 1 minus this y. And that's going to leave me with just x times dy dx. And then I just divide both sides by x. And all I'm left with is dy dx. Okay, I will promise you this. Whenever you use implicit differentiation, solving for dy dx should always be extremely easy, because dy dx will always be to the first power. It'll never be raised to a power. It'll never be in the denominator. It'll never be under a radical. It'll always be by itself. Maybe in several parts of the problem, but you'll have to get them all together, collect terms, throw everything else to the other side of the equation, divide both sides by the coefficient of x, just like I did here. The coefficient of dy dx was just x. Divide both sides by it, and you got it. Here's a formula for dy dx. All right, let's do it again. Another example. This time we'll make sure that it's more complicated. How about well, you know what? Maybe this is the time to do, well, yeah, maybe this is the time to do something that's really complicated. How about this guy right at the beginning? If I can get up there. Yeah, let's do this one. Okay, so what I want is, well, even that's not complicated enough. Sorry. We need something fresh. Okay, so let's try the square root of x plus y equals 1 plus x squared times y to the third. All right, that'll be complicated enough for now. Okay, I want to find dy dx, or y prime. So what do? Because this is an equation, this means that y depends on x. If I change x, I'm going to have to change y. So what do? I just take the derivative of both sides with respect to x. So the derivative of the left is the same as the derivative of the right. Now, some of you just love to run with problems and start taking derivatives and calculate. I highly recommend that you write this stuff out, d over dx of. And here is where it's very important that you know the difference between d over dx and dy dx. d over dx means the derivative with respect to x of. So you need an object. You need something to take the derivative of. dy dx means the derivative of y with respect to x. That's a complete phrase. A lot of people, when they do this kind of stuff, they will stick dy dx up here in front, and that's fatal. You are not multiplying both sides by dy dx. You are taking the derivative of both sides with respect to x. That's very, very different. So what we're doing here is taking the derivative of both sides with respect to x. This is not dy dx here. If it were, I'd be multiplying dy dx times the square root of x plus y. I am taking the derivative with respect to x of the square root of x plus y. Okay, so how do I do that? Well, I need to remember that the square root of x plus y is x plus y to the 1/2 power. So that's going to allow me to take the derivative. With the power rule, and the chain rule. The power rule would say that since I have a constant power here, I'm going to go 1/2 times x plus y to the negative 1/2. 1/2 minus 1. But the chain rule says, wait a minute, this stuff in here is not just x, it's a function of x. So you got to multiply by the derivative of what's inside. Let's just write it that way. Do it a step. The derivative of x plus y. Okay, that's enough for the left. Now what about the right? What's the derivative of this mess? Well, the derivative of 1 is 0 plus. Now I've got to take the derivative of this product. So obviously I've got to use the product rule. So the first part is easy. X squared first times. Now I got to take the derivative of y cubed. This is y cubed, not x cubed. What's y? Y all by itself is a complicated function of x. So you could think of that as a function of x cubed. That's what you see here. So how do you take the derivative of this? The answer is the power rule and the chain rule. You're going to go 3 times f of x squared. Well, f of x is y, so you're going to have 3 times y squared. So it's x squared first times the derivative of the second. Well, it's not just 3y squared because the derivative of this is not just 3 times f of x squared. The chain rule has something to say. Remember, you got to multiply by the derivative of what's inside. So you're going to get an f prime of x stuck on the end, or dy dx. So first times the derivative of the second, and the derivative of y cubed is 3y squared times the derivative of whatever is inside y, because y is a complicated function of x. So the chain rule tells you got to do that. Then plus the second, which is y cubed, times the derivative of the first, and now that's no problem. The derivative of x squared is 2x, because x is the independent variable. X is what you're taking derivatives with respect to. Okay, so I've now finished taking the derivative of the original equation, which looks like it's a big, long mess, but, well, no, I haven't. I'm sorry. I've still got this to do. Okay, so let's just continue. I've got to take this derivative still before I can do anything else. So this part I'm just going to leave alone. 1/2 x plus y to the minus 1/2. And what is the derivative of that? Well, the derivative of this is the derivative of the sum, which is the sum of the derivatives. The derivative of x is 1. So I got to take that, and then I got to take the derivative of y. But what's y? Y is a function because of this equation. X determines y. So the derivative of y with respect to x is not 1. It's the derivative of y, whatever that is. Okay, so that's going to be equal to this big long mess here. Let's collect the terms a little. 3x squared, y squared, dy dx, plus 2xy cubed. Okay, now we got to solve for dy dx. And to do that, I've got to see that dy dx is here and here. And besides which, it's entangled with all this mess. So I do have to multiply this all out to get dy dx. So let's go ahead and distribute this guy. So this is going to be 1/2 x plus y to the minus 1/2 times 1 plus 1/2 x plus y to the minus 1/2 dy dx. And this is equal to just what I had right there, 3x squared y squared dx plus 2xy cubed. Now we can put everything on one side that has dy dx and everything else on the other side. So this term stays here. This term has a dy dx in it, so it's going that way. This guy doesn't have dy dx in it, so he's going that way. This guy is just going to stay right where he is. So here's what I'm going to have. I'm going to have dy dx left. and I'm going to have this factor multiplied by dy dx, and this factor with a minus multiplied by it. So I'm going to start skipping some steps here. This term, when it goes over to the left, is going to have a minus in front because I got to subtract it from both sides. And then I'm going to factor dy dx out. And what that's going to leave me with is this guy, 1/2 x plus y to the minus a half. The dy dx is factored out. And then this is going to be over there also with a minus in front of it. So here's my minus. And then I'm going to have 3x squared y squared. It is. Multiply it out and see. You got dy dx times this, dy dx times that. Here's that one. And here's this one. When you move it over, you'll get your minus. Meanwhile, on the right, I've still got my 2xy cubed. But I also pick up this other guy, minus a half x plus y to the minus a half. And now, all I got to do is take this one mess here and divide both sides by it. So that's just going to give me dy dx equals 2xy cubed minus half x plus y to the minus a half divided by 1/2 x plus y to the minus a half minus 3x squared y squared. Bunch of nasty algebra, but look, I have a formula for dy dx. Now, it depends on y, depends on x, that's the cost you have to pay. That's because I never solved for y in the first place. I had no idea how to solve for y in the original equation. Remember the original equation? It's way up here somewhere. In this equation, I don't think I can solve this one for y. It's going to be too nasty. Because I'm going to have to tangle this y. I would have to square both sides. That's going to take this up to the 6th power. I don't think I can solve a 6th degree polynomial equation. Sorry. So there's no way I can solve for y in this. Nevertheless, I can tell you what dy dx is. And this is very important because when you know an x and a y, you can calculate dy dx at that point, so you can calculate the slope of the tangent line. So let's just do that for an example. This is one of the problems that I guess I'm not going to assign, but I could. It's the problem, this is problem number 27, which looks like this. You know, maybe I should have a new page for this. Okay, so the problem is x squared plus xy, xy plus y cubed equals 3. Oh, no, that's y squared, sorry. X squared plus xy plus y squared equals 3. And they're giving us a point 1, 1. And the problem says, use implicit differentiation to find an equation of the tangent line to this curve. So, equation of the tangent. Well, I'm not going to solve this for y. It would be a pain. I could do it, but I'm not going to. And they're telling you that this is actually an ellipse. And 1, 1 is supposed to be on the ellipse. Well, let's just check that out. If you plug in 1 for x and 1 for y, you get 1 here, you get 1 here, you get 1 here, 1 plus 1 plus 1 is 3. So yes, 1, 1 is on the curve. So we've got some kind of an ellipse going here. I don't know what it looks like really. And 1, 1 is on there somewhere, and we want the equation of the tangent line. So if 1, 1 is over here, the equation of the tangent line would be with a positive slope. If it's here, it's going to have a negative slope, and so on. I have no idea where 1, 1 is on this curve because I've not graphed this guy. Nevertheless, I can figure that all out without much work because I will just take the derivative of both sides. I recommend that you write d over dx of both sides so that you know what you're doing. You're taking the derivative with respect to x of both, not dy dx It's the derivative with respect to x of the left side, which has to be the same as the derivative with respect to x of the right side if these two sides were to be equal to begin with. Okay, so let's take the derivative. Well, on the right, obviously, we're going to get 0. That's good. On the left, the derivative of x squared. Well, x is the independent variable, so this is not a problem. Derivative is 2x. Now we get x times y. We've done this one before. This is a product rule. So once again, it's the first times the derivative of the second. The derivative of y. Y is not x. Y is the dependent variable. So the derivative of y is just the derivative of y, whatever that is. First times derivative of the second plus the second times the derivative of the first. The derivative of x is just 1. That's not a problem. Now we got something more interesting. What happens with y squared? What is y? Y is some horrible complicated function of x that I haven't solved for. So what's the derivative of y squared? Well, the power rule says the answer is 2y. But y is not x. Y is a function. So the chain rule has something to say. You got to multiply by the derivative of what's inside. The derivative of what's inside y. So we got to multiply by dy dx. Okay, so this would allow me to solve for dy dx. So let's go ahead and do that. Anything that has dy dx in it stays on the left. So this stays and this stays. Everything else is going to go. So I'm going to have, and while I'm at it, I'll go ahead and factor. So dy dx is going to be multiplied by, over here it's x, and over here it's 2y. And then the rest of this stuff is going. So I'm going to get minus 2x and minus y. So here we go. Dy dx equals minus 2x minus y over x plus 2y. But I'm not really interested in dy dx everywhere. I'm interested in dy dx at 1, 1. So when x equals 1 and y equals 1, dy dx at that point, which would be the slope of my tangent line, is going to be minus 2 times 1 minus 1 over 1 plus 2 times 1. And what is that? That's minus 3 over 3. That's minus 1. So I got it. The slope is minus 1. My equation is y minus 1 equals minus 1 times x minus 1. And there we have it. Now, in the next lab, which we're not going to see this week because we're going to be on fall break this week, we're going to be doing a lab on implicit differentiation, even though we will be away from implicit differentiation. But you will be able to see that you graph this thing. Maple is decent at graphing implicit plots. You can plug this into Maple, and Maple will graph it for you. And then you can see that this equation, which you can plot, actually hits at the point 1, 1 and is tangent to that curve. So it's kind of a powerful technique. Okay, that's it for this particular lecture. We do have more things that we're going to be using implicit differentiation for, some things that you might not have expected. So yes, there's going to be another lecture on implicit differentiation and another day spent on problems like this. So see you later.